Hello, everyone, and thank you for joining us. My name is Juliet, and I will be the moderator for today's webinar. Before we dive into the content, let me cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. All tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your presentation area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any audio or video issues, you can find answers to some common technical questions located in the help widget at the bottom of your screen. Please note that a copy of today's slide deck and additional resources are available in the resource list. Please have a look and download everything that you may find useful. Also, the webinar will be recorded and sent via the email you registered with. Lastly, if you have any questions during the presentation, you can submit them through the Q&A widget. We are here to answer you live via the chat, so don't hesitate to reach out throughout the presentation. Now, I'll introduce our speakers. Today, we're joined by Dr. Saulius Pavalkis. He is a world-class top MBSE expert working as a global MBSE ecosystem director and MBSE R&D cyber portfolio manager for North America at Dassault Systèmes. He has 20 years of MBSE solutions experience as an MBSE transformation leader, product owner, and analyst at Cameo core team. Throughout his career, he has been actively involved in building world-class MBSE solutions and supporting MBSE's adoption in major aerospace and defense and transportation companies. He's contributed to MBSE's SysML-based method and framework, Magic Grid, and more recently, Agile MBSE Cookbook by Bruce Douglas. Saulius guides 4,000 plus subscribers on YouTube, the channel MBSE Execution, the largest SysML systems simulation community. You can find the link in our resource list. Through the work, he has accumulated major experience in systems modeling, simulation, MBSE ecosystem, interfaces, integrations, traceability, and queries. We are also joined by Cary Bryczek. She is the Director of Solutions for Aerospace and Defense at Jama Software, with a focus on the specialized business and technical needs unique to this market. She helps lead the company in systems engineering and MBSE domain. She has over 25 years of experience leading systems engineering in the aerospace and defense industry with roles at the U.S. government, Lockheed Martin, PTC, and Jama Software. She is a member of INCOSI and a member of the Women in Aerospace organization. Outside of work, she enjoys playing jazz guitar and gardening around her farm, which sometimes requires the operation of tractors and UAVs. And with that, I'll pass it over to you, Cary.
Oh, thanks so much, Juliet. I am truly looking forward to your presentation, Saulius. To kick things off, I want to set the stage with some trends across the A&D industry that we're seeing. I'll talk about how those trends are creating challenges for chief engineers and describing what keeps them up at night. Then I'll set the stage for Saulius's presentation by showing you what Jama Connect Traceable MBSE looks like and how it's designed to solve those challenges. Saulius is going to take you on a deeper dive to show you how system models and Jama Connect interoperate. So in the aerospace and defense industry, we are developing a new system that has complexity that far exceeds commercial product development. For example, the FAA's program to develop the unmanned aircraft traffic management system involves not just a pilot, his drone, but is designed to enable autonomous and semi-autonomous operation of multiple air systems, including the passenger and cargo delivery in a really tightly integrated civil airspace. The elements in blue on the diagram are all distinct systems of their own. And the new traffic management system, needs to integrate communications and data across all of those systems to provide this new capability. In the highly constrained environment of outer space, for example, NASA's Cislunar, and I'm pretty sure the Artemis programs as well, are focusing on the operation and survivability of autonomous systems. To develop a space system, NASA doesn't do this in their own silo, but they have lots and lots of contracts and companies that they work with to deliver parts of the system, just like in the DoD. For example, you have Blue Origin, they are developing a friction stir additive manufacturing part of the system in partnership with Langley, right? You have Redwire out of Erie, Colorado. They are developing another in-space manufacturing system. You have Canopy out of Denver. Colorado seems to be a popular place for space. They're developing low-cost, reusable thermal protection systems, right? And there's really dozens more. The Cislunar and the Artemis programs are developing ecosystems and the ecosystems of those partners, right? In the government agencies and the aerospace and defense companies, they're always evolving their strategies to be able to deal with this high degree of complexity to help streamline their engineering processes. For example, the DoD, they have published a new adaptive acquisition framework. So even not just in the engineering parts of it, but the acquisition parts of it as well, there's a new framework. This particular pathway is intended for large-scale traditional hardware acquisitions to help facilitate rapid and iterative delivery, kind of like what the software capabilities programs are doing. In 2018, we had the digital engineering strategy outlining a vision to modernize how DoD designs, develops, delivers, operates, and even sustains systems, right? By connecting people and process and data and developing these end-to-end digital enterprises. The International Council on Systems Engineering, their Vision 2035, is intended to guide and inspire the strategic direction of systems engineering for the global systems engineering community. Right? The DoD's Systems Engineering and Architecture group within the DoD itself is focusing on modernizing the systems engineering practice, and they're leveraging the capabilities coming out of CERC and MOSA to build systems that can be upgraded to incorporate new technology and respond to emerging threats. Right? With this new modernization of the SE approach, I know this is sort of an eye chart. You guys can look at it after the fact, right? The DoD has moved away from visualizing its process using that shape of the V model in favor of what more realistically takes place from a process standpoint, which is that modern systems engineering is highly cyclic in nature. The outermost ring is as close to what the old Vita model, where concept definition is in the upper right, moves to, or the upper left, right, moves to system definition through architecture and design over to V and back around to start the next cycle. What's important is that there's a strong emphasis on measuring, not just the system being built, but the process to build that system. And that data and models are at the heart of it all, right? To the fullest extent, models should be used in favor of documents, and data should inform the decision-making. There really is a challenge to using a data-driven approaches and models. The DoD, I love this quote, there's a lack of an integrated approach to implementing systems engineering focus areas that's creating a delay in implementing the digital transformation, which is necessary to ensure relevant guidance, skills, and training are available to deliver this, a disciplined approach to, acquiring a weapon system. Continuing to use legacy tools and approaches is what making integrated approaches gravely difficult. What's necessary is to take a federated approach to data across the tool ecosystem and use tools with robust APIs, modern architectures that are standards-based. An MBSE approach requires an integrated approach to connect that system models architecture and requirements to program teams and software and hardware teams. It doesn't mean using a siloed system modeling tool and expect those teams to be able to consume and understand that model. In fact, kind of what I hear a lot is, how do I achieve the benefits of MBSE when no other engineers can access model parameters they need to use to make, downstream decision making? Right? And how do I make, decisions on tests and, other things that's downstream from the system model? I hear that quite a lot. Those with technical oversight and responsibility for program success who are executing MBSE or even just traditional systems engineering, commonly raise these following questions. This is what I think, keeps chief engineers up at night. How do I know if the architecture and system requirements are satisfying all the needs? How do I know if a change in the architecture will impact those needs? How do I know if a change in the architecture will impact hardware or software teams? And how do I streamline model design reviews? I have a fourth one too. How do I detect unallocated systems architecture and requirements? So that sort of transcends the system model area and goes into the software models and the hardware models. So that's another favorite that I have. So these questions really, we think, can be answered using what we term traceable MBSE. The reality at most companies is that the end-to-end systems development process is fragmented into domain-specific tools and spreadsheets that really don't have a lot of collaboration or any of, and this leads to fragmented requirements traceability and requires significant manual effort through emails and meetings and maybe even luck to try and prevent delays, defects, rework, cost overruns, right? Most companies have come to accept this situation as an unchangeable reality, given the lack of a single platform to enable this entire process, nor a method to integrate spreadsheets and desktop tools. Using traceable MBSE, the system model in the modeling tool is joined with the Jama Connect model. Jama is continually calculating traceability and coverage and provides scores that can be used to identify high risk areas that can be drilled into to determine corrective actions. The system model can detect those changes and the modeling engineers can take corrective action. Keep in mind that model-based systems engineering is more than using the power of SysML. It is powerful. Systems engineering's superpower to enable digital transformation comes when it's able to connect to the entire development effort and facilitate, software and mechanical teams with the ability to align their efforts to the system model. Systems engineers being able to manage the state of development across the disciplines, and automatically identifying risks through all stages of development. So let's maybe see what this looks like in Jama.